All right, finishing up our review here on 30, asking us to label these as ionic, polar covalent, or non-polar covalent. To distinguish between the three of these, first of all, if it's ionic, we're going to have a metal and a non-metal. So the easiest way to figure out if it's ionic is to figure out, is there a metal present? If you go through and look at each of these, I want to figure out if it's ionic or covalent. The only ones that have a metal in them are going to be C, which has sodium. So that one's ionic. D has magnesium, and that's ionic. So the rest of these cannot be considered ionic. They're going to be considered covalent because they are nonmetals or a mixture of nonmetals put together. If it's polar, this is one of these things between polar and nonpolar. It gets a little bit foggy in terms of being able to evaluate because, I mean, you could look it up if you actually had to answer this question. There's kind of an agreed upon way to do it. But unless you have access to a chart of electronegativities, or you have that chart memorized, or you've just got some certain things memorized, it's really hard to know if something's going to be polar or non-polar without being able to look them up. Rule of thumb is they're going to be polar if you've got different nonmetals. They're going to be non-polar if you have the same. Now, again, this is not completely factually true, but for a basic chemistry course, that's usually good enough for me. So if I go through and look at these, HCl, these are going to be two different. All right, so HCl is a component for hydrochloric acid. Again, you've got two different nonmetals on here. Since we got two different nonmetals, there's going to be a difference in the electronegativities, which is going to lead to some polarity. So this would be polar. On B, I've got two oxygens that are stuck together. Since I've got two oxygens that are stuck together, neither one of them should pull on electrons more than the other. Therefore, it's going to be nonpolar. Jump over here to E, I've got hydrogen and oxygen. Again, I've got different nonmetals, so there's going to be a difference in electronegativities. Typically, in this case, we would describe water as polar. Oxygen is going to be more electronegative than hydrogen. The last one here technically is usually described as nonpolar. However, we do have carbon and hydrogen, so if you followed my rules up here, we would probably end up calling this polar. There is some slight polarity between the carbons and the hydrogens, although it's not very large. So by rule, as far as chemistry rules go, this is typically going to be described as a nonpolar molecule due to the very slight difference in electronegativity between carbon and hydrogen, and also the geometry of the three dimensions, the way the molecule is put together. So I can't speak for other teachers. If you were in my class and you called this polar and you told me because it's two different nonmetals, I'm perfectly good with that. If you're in someone else's class and described it as nonpolar because you said the electronegativities between carbon and hydrogen were very small, and also because of the geometry, the electrons really don't get pulled into one area. Yeah, that's probably a better description as well. But for an introductory chemistry class, I'm okay with this being called polar, although it's technically not. All right, 31, wrapping this up, it says balance our equations and identify the type of reaction. So let's start with the type of reaction. We've got 5 different ones. The 5 reactions we have typically, if we look at what we are starting with in the reaction and what we end up with, we can usually figure out which one to classify it as. On the first one, I've got an element and a compound. And so usually by definition, if I've got an element and a compound together and I end up with a compound and an element on the other end, this is going to be a single replacement or a single displacement reaction. Single is always going to have just an individual single element by itself at the beginning and an individual single element by itself at the end. In this case, hydrogen does say H2, but that's because hydrogen's always diatomic and it sticks to itself. On B, I've got a compound that's breaking apart into two simple or just individual elements. This is a decomposition. C, I've got a compound and a compound turning into two more compounds. This is real similar to the single replacement because in the single replacement, zinc and hydrogen switch places. In this one, barium and sodium switch places. So this is also a replacement, but it's a double replacement. And remember, metals replace metals, nonmetals replace nonmetals. We scroll down to these last two on D. D is kind of the opposite of a decomposition. I've got two elements at the beginning, and I've got a compound at the end. So we are making something bigger. That is a synthesis reaction. The last one, E, I've got two things turning into two things, and this is the one where we pay particular attention to what is in them. And so in E, I've got a hydrocarbon, which in this case C6H12, combining with oxygen makes carbon dioxide and water. Those are all the ingredients and outputs for us to burn something. And so we would have this described as a combustion reaction. So those are our 5 types of reactions. If we want to balance them, then we need to go back and probably start writing some numbers down. The foolproof way to do this is let's count everything. So on 31A, I've got 1 zinc, 1 hydrogen, 1 chlorine, and I'm ending with 1 zinc, 2 hydrogens, 2 chlorines. It's clear that I need more chlorine and I need more hydrogen at the beginning. So I need to increase both of those to 2 if I can. And I can by simply putting a 2 there. Changes both of those into a 2. And this one is basically done. Remember, we don't need to put 1s in here. In chemistry, typically we don't write 1s. If there was 2 of those, I put a 2. I don't write a 0 because a 0 would mean it doesn't exist. There's no reason for it to be there. Okay, so on B, clear this up, get the clutter out. Same thing, let's count. 2 aluminums, 3 oxygens. I end up with 1 aluminum and 2 oxygens. So this is one where you can start in different places. I need more aluminum, I need more oxygen. I'm also got this weird combination here of 3 and 2. So when we balance elements, they're always going to increase, and they're always going to increase in multiples of that number. So because I've got 3 oxygens over here, eventually I'm going to need to have 3, 6, 9, 12, 15, some kind of multiple of 3. And the same thing over here with oxygen, because this is the only place I have oxygen. Anytime I put a number in here, I'm going to be multiplying times 2. So it's always going to be 2, 4, 6, 8, 12, or whatever. Based upon that, that means that these two numbers, 3 and 2, if I want to get them to be the same, the first number that they're going to hit together, if I multiplied them, 2, 4, 6, and 3, 6, would be at 6. So sometimes this is a quick way to do a 2 and a 3 is to figure out what's the first number they're going to both multiply into, the least common multiple, I believe is what we call those. So in order for me to turn these oxygens into a 6, I would need to put a 3 here. In order for me to turn these oxygens into a 6, I would need to put a 2 here. Now notice by putting the 2 in the front, it also increased my aluminums to 4. And now everything's balanced except for this aluminum on the right-hand side, which I need to turn that into a 4. And I can do that by putting a 4 there. Okay. You could have gotten the same answers without doing this step where I did, going directly from 3 and 2 to a 6. But if you've got a 2 and a 3, you're eventually going to have to turn them at least into 6s in order for them to be balanced. And then on C, C's a little bit more complicated. It looks like there's a lot of elements in here, but one other little shortcut is realizing that we've got some things off the back of the periodic table like NO3. So I don't necessarily need to count all of these separately because this NO3 sticks together as NO3. Same thing with this SO4. The SO4 stays SO4. So what I'm going to do is actually just count ions. So I've got 1 barium, I've got 2 NO3s, I've got 2 sodiums. I should have scrolled down to have a little more room. And then SO4, I've got 1 of them. Remember, just kind of looking at the entire unit. And then on the other side, I've got 1 barium, 1 SO4, 1 sodium, and 1 NO3. I like to go through and circle what I need more of. So if I start with 2 sodiums, I need to end with 2 sodiums. If I start with 2 NO3s, I need to end with 2 NO3s. The only thing I need to adjust is this Na and the NO3. Fortunately, they're already together, so I need to change both of those into a 2. I can do that by putting a 2 there, and that should balance that equation. Now, if you went through and wrote out all the N's and the O's and everything that are part of the polyatomics, you would have gotten those as well. But oftentimes when you have a polyatomic ion, in other words, one of these things that's on the back of our periodic table on the chart, if you just kind of think of it as a clump, because they're always going to stick together. The NO3 is going to stick together as an NO3 if it's one of those substances. All right, and then D, nice and simple. I start with 2 hydrogens. I start with 2 nitrogens. I end with 3 hydrogens. I end with 1 nitrogen. You notice I need more hydrogen and I need more nitrogen. Again, this is a 2 and a 2-3 again. So again, my 2 3s, I know I need to change into making both of them 6s in order to balance out. I can do that by putting a 3 at the beginning, because 3 times 2 gives me the 6 here. I can do that by putting a 2 here, because 2 times 3 gives me the 6 here. That also doubles my nitrogens, and in the process, balances the equation completely. And finally, with the last one on E, my combustion reaction, I've got 6 carbons, 12 hydrogens, only 2 oxygens, and on this side I have 1 carbon, 2 hydrogens, and here's where you got to be careful with your oxygens. There's 2 oxygens here, 1 oxygen there. Put those together, that ends up being a total of 3. All right, so if I look at what I need more of, I need more oxygen on the left, I need more hydrogen on the right, and more carbon on the right. Now this one, because I know in the previous I'd been changing the 2 and the 3 into a 6, I'm going to leave the oxygen for last because the oxygen split up over here on the right. And it just gets to be a little bit more confusing. It's pretty easy for me to fix the carbon and make it 6 and 6. So if I want to turn this into a 6, I can put a 6 in the front. Okay. Notice though, it also changes my oxygens because now I don't have 3 oxygens. I've got 3 times 2, 6 times 2 right here. 6 times 2, which is going to be 12, plus my 1. And now I've actually got 13 oxygens on the right hand side. I can balance my hydrogens. I need to turn the 12. So there's 12 on each side, so I need to turn this 2 into a 12. I can do that with a 6 on the front because 6 times 2 is 12. Again, that changes my oxygens. Now I've got still have 12 over here, but now I've got 6 on this side. So my 13 has turned into 18. Now my carbons are balanced, my hydrogens are balanced. The only thing left is my oxygens. I need to turn this into an 18. I can turn this into an 18 by putting a 9 in the front because 9 times 2 ends up being 18. And now that balances the oxygens. Everything is done. We have some balanced equations.